if you were, again, right there with just a bird's eye view, just sitting there. And wow, there's a lot of stuff going on. So what do you see? First thing I think you might see are alternating jets. What are those? What I mean is there are jets of fluid, some moving in what's called the red direction, prograde. It's not actually red, but everyone draws prograde as red, faster than the planet. Do you see that all those parts are speeding by faster than the planet? If it was going the same rate as the planet, it wouldn't be moving in this frame because we're in the frame of the rotating planet. So there's tons of parts that are going faster, and there are also a number of regions that are going slower. Those are called retrograde jets. Okay, so now I often get asked, wait a sec, what's a jet? So let's step back. What is a jet? Here's a delightful jet in Lake Geneva. It's a water jet. They've got a huge pump there, and it's firing water like 100 meters in the air. So it still begs the question, what is a jet? A jet is a focused, high-speed flow of some fluid. It could be gas, it could be water, it could be whatever you want it to be. Here it's water. But it doesn't have to be. A jet is still a jet, even if you're just talking about gas, let's say, in a planet's atmosphere. We have the jet stream on Earth, for instance. Okay, here's another jet. That's a jet. That's a localized, really high-speed flow. And if you look in this eddy, there's actually really slow flow over here. If you look on that side, it's really slow. In the middle of this stream course, Rock Creek, it's flying. That's basically a jet. And I don't mean to curse anyone with bad luck here, but in the next couple weeks, there may be some overflow of some of our banks in this region. You will see really quiescent pools and marshes, right? And in the middle of those quiescent flows, there'll be really fast streams. Those are jets. Are you with me? Okay, good. So that's what a jet is. And that's still maybe an easier picture. And so we'll take that picture, that's a jet, and let's tip it over. Those are our jets. I'm going to hammer you with this. One jet, another jet, jet, retrograde jet, prograde jet. Is everybody with me on what a jet is? Good. Okay. And so now if we measured, what scientists do is they get this incredible set of images. These are, I think, from Cassini. And they track these clouds. And once you track them, you can then build a map of the velocities. And so these are velocities with respect to this black line here corresponds to this white line here. If things were right on this black line, they wouldn't be moving on Jupiter. They'd just be sitting there. But instead, you see these local jets, and there are about 30 of them going prograde and retrograde, prograde, retrograde. That's crazy. We do not have that on Earth. You guys buying that? You can see it in the movie. Earth, we have a few jets, but maybe 5 on a good day. Here we have about 30. And they're much stronger in contrast to what we have on Earth. Okay, what else is there with the weather? Vortices. What are vortices? Vortices are localized flows that wrap around themselves. Whereas when I'm talking about a jet on Jupiter, I'm talking about a flow that wraps all the way around the planet along a line of latitude. In contrast, a vortex, how about that one, wraps around itself. So we can see tons of delightful vortices on this planet, the most famous one being the Great Red Spot. Earth, you can fit 3 Earths across here. That is a large storm. How old is it? We don't know. It's as old as we've been observing it. So when Galileo first looked at Jupiter, it was sitting there. And it's been hanging out ever since. And it's had some variation now that we have really high cadence measurements, but it so far has been pretty healthy. And so this is a very long-lived, very stable system. And I want you to kind of keep in mind, if you go and play with the record players afterwards and make a vortex or two, when it's rapidly rotating, look at how long the vortices last. They're completely stable. Okay, so big questions. Structure, pretty interesting. Surface flows, interesting. What do I love, though? I love what's going on in there. So let's start looking underneath the cloud deck. And if you look underneath there, you could see we have all these great flows. We just look at cute movies. They're wonderful. Are those flows just living in the cloud deck, in that top 50 kilometers like we have on Earth? Or do they go deep? They could be in the shallow part, or they could go all the way down to where the fluid metallizes. And actually, we can't tell the difference. Not we can't. We have various theories, and just like I said with people who argue about if there's a core of the planet or not, with the flows, there's some people who look at the surface flows and they say, oh, those go all the way down to the dynamo, to where the magnetic field's built. And there are other people who say, clearly they only exist where the clouds are. And we've been arguing about this. I'm a deep person. I have friends who are shallow people. But it's almost this partisan divide. It is very sharp. And we're arguing about it. And we've been arguing about it now for about 60 years. So it's fairly long-lived. Okay, so how do we provide answers? Who wants to be stuck forever? So there are two ways that I'm going to talk about today. One is, if we really want to know how things work on and in this planet, if we want to know if it has a core, if we want to know all these things, we should go get good data. So the first thing I'll show you is some info on the Juno mission, which is right now orbiting Jupiter. Then after that, I'll talk about experiments. Maybe I'll even get to our Jacuzzi. Okay, so I'm going to play you some stuff I found on the Juno site. Hopefully, they will do a better job explaining themselves than me.
After 5 years of being alone in space, Juno approaches Jupiter and begins reaching a top speed of 160,000 miles per hour, officially becoming the fastest man-made object in history. The main engine ignites to slow down the spacecraft, and Juno is captured by the powerful gravitational pull of Jupiter. Settling into the most challenging orbit ever attempted, Juno will come as close as 3,100 miles to the planet's cloud tops. Juno will continually duck below deadly radiation belts as it studies Jupiter in unprecedented detail for more than a year.
Okay, cool. So wait, let's do one more. So that's Juno, and it's there right now. It's in orbit. And let's just look. I like the other thing they put out on what's Juno going to study.
Will help prove or disprove theories about the types and amounts of materials that contribute to the composition of Jupiter.
I didn't even mention that.
By peering beneath its clouds and discovering what Jupiter is truly like, Juno will also test our ideas about the formation of planets, as well as other major secrets of our solar system. Measuring the amount of water in Jupiter will help us understand how and where in our solar system the giant planet formed. Mapping the gravity and magnetic fields of Jupiter teaches us about the planet's hidden interior and whether it has a solid core. In our quest to unlock the history of the planets, Jupiter is the gateway, and Juno holds the key.
Okay, cool. So Juno is this fabulous mission. It's in orbit right now. If you could, I think you could tell they showed some of its paths. It's on a polar path. So it's on this polar path that goes over the North Pole and the South Pole. And every time it does, it gets really close to the planet. So it gets very detailed data on what's happening. Both the gravity field, it can measure the heat coming out. It can measure the magnetic field. It can measure a lot of things. So far, though, it's only done a few passes. So really what we've got right now are images. And it's interesting. This is an image off of JunoCam. And JunoCam was the thing they put the least money into. They really wanted the data, which I get, but come on. I mean, the images are worth their weight in gold. And I think the members of the Juno team would argue this already is worth its weight in gold. So let's take a close-up of this, and you can see that's just awesome. So there's a lot going on there, but again, what do we see here? Here's a delightful vortex. Here are what are called filamentary structures. And I want you to see how teased out these are. And yet, They're stable. You see those kind of filamentary structures, any image you see of Jupiter. They don't get mixed out. That's kind of what we saw over there. So again, afterwards, if you can, go play. See if you can make filamentary structures. Now, here, you see these little white dots. Anybody know what those are? They're clouds. Those are water clouds. So that's us. Looks like there are some, I think it's water. I got to check again. It might be ammonia. It might be a lot of things. But those are Earth-esque clouds, and they are just tiny. We couldn't really see those in previous images of Jupiter. We just see the large scales. Now that we have a very low altitude flyby, we see all this other stuff happening. That's a close-up showing. Look at that beautiful vortex. Nice vortex, some different chemistry being dredged up by the vortex, and around it, these tiny little structures, bigger structures, much larger. Again, Earth is, it's close. It's a little bigger than that, actually. It's more like that big. But this is a big planet. And I like that because you can see the curvature of the planet there. Very nice. Okay, so what can I tell you right now from the Juno mission? Not that much, because right now they're really in picture mode. They've only done, I think, 5 flybys out of, I think it's 50. And so they've only mapped a little of the planet. But already, just the images they get are nothing like what we've seen before. So, okay, so great. We have very beautiful pictures. We have a very beautiful planet. I now want to go into some experiments and start to learn some of the physics of the basic fluid mechanics occurring on a Jupiter. Then we'll come back and look at some of the pictures again and try to interpret them in terms of what we know. Does that make sense? All right, okay. So now let's go on to some experiments. And so here's some planet. We're going to cut it away. And we're going to do experiments just like we did there. We're going to do them again. I think they're worth it. Let's do a stationary planet. And I'm going to dump in, like usual, some creamer. We saw this already. It just drops like a rock and sinks and spreads. It's like an upside-down atom bomb, right? You see a mushroom cloud. The physics is the same. It's just dense stuff sinking instead of light stuff rising. Now let's rotate rapidly. It's been rotating for like half an hour. I pour it in. It's what you saw. We all saw this. But look at how different that flow is. Now we get an axialized, which means aligned with the rotation axis, an axial vortex. And that thing's super stable. So why did it do that? I was trying to say before, it's because the fluid is all now acting like a big gyroscope. And just like a gyroscope, you perturb the fluid, it doesn't want to tip over. Well, in the previous one, you could think of it this way. In the previous one, the energy in the fluid, when it was non-rotating, it's like the fluid it did. It all fell and got as low as it could. That's what happens if you take a top that's not spinning and drop it. It just falls over. Here, when it's spinning, it can't sink. Instead, it starts rotating like a top. Are you guys with me? I'm being very heuristic, but that is actually even mathematically correct. Okay, so let's look at them again, just because they're so great. Non-rotating case, top view on the bottom. So polar view on the bottom, side view on the top. Cool. Very quickly, everything's just flat. Non-rotating flows, everything's 3D. Everything's moving in all 3 dimensions. Everything settles really quickly. And it's basically what you'd see in your sink. Everybody knows this. Deep down, you kind of know this flow. You see it and you go, I know that. I poured stuff into the sink. Or into I poured milk into a full container by accident in the sink. Now we do it again. Here's top view as well as side view. And you have a localized axial vortex. It's so cool. And stable. And so in a rapidly rotating case, everything aligns. Here's the hard part. It's a little technical. The flow stays quasi-2-dimensional. What does that mean? Okay, what I mean is, it's one big spinning structure. And if it's spinning the same at the top, if we did that experiment the size of this room, you'd see the stuff moving at the top moving at the same speed as the stuff at the bottom. It'd be one coherent structure. Well, if it was, in some sense, it'd be two-dimensional. If the motion at the top is the same as the motion at the bottom, then the motion, the field of velocities, is not varying in this one direction along the rotation axis. So in that sense, the flow field is two-dimensional. Does that make sense? It's weird. But that's the idea. So it's quasi-two-dimensional. It's not exact, but it's true. In addition, it's just incredibly well organized. Everything's very coherent. Lastly, it doesn't settle. Why? Again, because it's like a gyroscope. Just like a spinning top doesn't fall over, but instead spins, this fluid starts spinning, and it doesn't settle. Okay? I'm going to use that as a model a lot, as my base idea. So, okay. So those are what we get from experiments, from simple experiments. Now, let's kind of mesh the two together. All right. So here's a nice picture from Juno. It's got some vortices in it. I hope you can see. Right along in there. It's got those filamentary structures, and within them, there are little round spots. Those are all huge vortices, and in between them are these filamentary flows. Okay. I just wanted to mention, you might be saying, oh, okay, they're beautiful, but why would we go all the way there? Why go all the way there just to get a close-up picture of a nice filament? Okay, here's an image. Where's this from? Yeah, that's Earth. Where? What am I looking at? Any guesses? Good. Oh, yeah, river delta. Good idea. No, good. Might look like an oil spill. That is a phytoplankton bloom in the North Pacific. So that's primary production. That's climate, in a sense. Do you know what I mean? That's life, and that's how Earth's whole system is working. So what I love is this is the ocean with biological activity happening in it. What's mediating where the activity is happening? The fluid dynamics. What do you see? You see flows that look a lot like what you see on Jupiter. These are rapidly rotating flows. Flows in the ocean are pretty slow, and the Earth rotates fast. So the zeroth order dynamics you see in the ocean, they're not that different from Jupiter. And if we're going to understand Earth, you also better be able to explain a Jupiter. Do you get it? And so this is what people do. They take their models and they say, I think I'm so smart. I even think I can do Jupiter. And then they port it to Jupiter and it doesn't work. And then they say, oh, I have to improve my model. And back and forth. Do you get it? Okay, so this is, I forget where it was. Yeah, it's Pribilof Islands. Yep. And it's from NASA Earth Observatory, probably the MODIS 1 satellite. Okay, so there are vortices. How do we explain them? Okay, I'm going to explain them again heuristically, and I'm going to do it using, yes, another experiment. So this is a bigger table that we built, again, for outreach demos, but it's actually working pretty well for showing the basic physics. And so it's a rotating table. It's been rotating for a while. Guess what we put in there? Sam May, who used to work in my lab, put in blue, yellow, and red food coloring. It's just a lot bigger, but it's no different than these. About 5 centimeters of water. And now we let people come and truly be the hand of God. We just say, put your hand in there. When you put your hand in there, you're generating flows that are as fast as the tank itself. Well, when your hand is actually moving it, minus the rotation rate of the table, if you were living on the table, it just messes up everything. It's super turbulent. And then rotation isn't actually that dominant. So what you'll see here, that's actually more like what we have, not in Earth's ocean, but in Earth's atmosphere. Flows in the atmosphere are fast enough that they're rotating, but turbulence sometimes takes over.
Hands out, hands out.
Whoa! Whoa!
And so everything's mixing right now. We'll give it a second, but we'll see what happens.
Oh, wow. Yeah.
Cool. Does it look like Jupiter? I'd say no. It looks a little, but I'd say it's messier than Jupiter, honestly. And maybe I'm being too simple. There is some large-scale structure, but really it's so turbulent from them having put their hands in, it's not that Jovian, the vortices. Now, let's run it again. And I'll let Sam talk, and I'll let some kid talk who is standing at the table. Let's run it again. And now this next iPhone movie I took was about 30 or 40 seconds later when the flow had slowed down a bit. When it slows down, look what happens. Rotation takes over again, and you start to look a bit more like Jupiter.
That does look like Jupiter. All those small tornadoes and a superstorm.
Cool. That kid's right. Whoever that kid was, spot on. So now what happened as the velocities got a little slower, once we'd taken our hands out for a while, some of that turbulent energy radiated. It's still actually rapid flows. It's still what you would call turbulent. But now rotation and gyroscopic physics has taken back over, and you get these big, beautiful, coherent structures. And do you see filaments? They're all over the place. Okay. Why do you see filaments? Because the flow is now 2D. And so when the dye runs past each other, it's just this 2D kind of passing of ships in the night. When it's 3D, they all mix together and you just get a mess. But the minute it becomes gyroscopic, you start getting the filaments, you start getting the big structures. Does that make sense? I'm being heuristic, but that is a 0th order good explanation of Jupiter. So let's just look again. No sound. Messy. You might notice colors are mixing there, where streams are coming together. But then, by a minute later, everything's settled down, you're Jovian. Cool. Okay, good? All right. So now, what do we need to explain vortices? We need really turbulent flow, and that's what we have on Jupiter. And we need even more so the dominance of rotation so that we get that gyroscopic physics, okay? That's all I'm going to say about vortices, but that's my 0th order explanation of what you'll see on these planets. Now, let's head over finally to jets. Okay, what do we need for jets? Massively turbulent flow, even stronger rotation, and what else? We need more ingredients. We need to have a non-planar system. Remember somebody mentioned before what happens when it goes fast? We said we get a paraboloid. That's a system with curvature. What else is a system with curvature? A planet. Planets are spherical. They're curved. They're not flat. But all my experiments so far have been flat. It's okay. So you won't get jets in any of these experiments. You'll get vortices because they don't have curvature. And the curvature adds one more level of physics. And so let's see if we can walk through it. It's okay. Here's my simple image of a planet. I'm going to argue we have deep jets. Why? I'm a deep jet person. It's who I am. You can't get away from who you are. So I love the idea of deep jets. I think there's turbulence throughout like the outer 10,000 kilometers of Jupiter. And I have noticed that Jupiter, that region is a spherical shell, so it's got curvature. Good. Those are the ingredients we need. And I'm arguing that's all we need. Why is it turbulent in there? It's turbulent for the reason I mentioned before. There's as much heat leaving Jupiter as is coming from the sun. That's a huge amount of heat. With Earth, the heat coming from the sun is like 10,000 times the amount coming from below. On Jupiter, it's 1 to 1. So there's a lot of deep convection coming up. And that drives all this turbulence, and that turbulence should still be gyroscopic. So if we make a numerical model, this is an image from my collaborator, Thomas Gastine. He made a model of something like a Jupiter, maybe it's Saturn. And we're looking at the convection in the outer, maybe it's 20% of the sphere. And we're looking at the temperature field. Red means hot, black means cold. So this is the structure of convection, and here's a cutaway in the equator. And so this maybe looks like standard hot and cold stuff mixing, but when you cut away along this line of constant, I guess it's longitude, you see all the flow structures are aligned vertically with the rotation axis. So even though this is now a spherical shell with spherical gravity, the flows are still gyroscopic when you rotate the system fast. Is that strange? That's weird. You wouldn't guess. I wouldn't guess that. You wouldn't guess that. Except we've done the experiments. We've lived it. So, okay, maybe it's not so crazy. And so this gyroscopicness sticks around. It stays around. So now let's think about it. Okay, next level. So now we've got all this fluid, it's all living on these quasi-two-dimensional elongated structures. And now those structures are living within a spherical shell. So if I go some distance from the rotation axis, that distance is called s, but whatever. If we go that distance s, then you would say, oh, the local column height is h. That's how tall they are. Now, what happens if somebody perturbs this column of fluid? It's gyroscopic. It wants to stay 2D. But what happens if we move it slightly farther out in the shell? What happens to it? It gets squashed. If you move it further out, it's a column of fluid. We'll say I'm that column. If you moved it further out, it does not want to stop being 2D. It wants to stay in an aligned column, so it's going to get squashed. Are you with me? If we pull in towards the center of the planet, towards the rotation axis, what's going to happen to me? I'll finally be a 6-footer. Thank God. Good? Okay. So now, let's do some physics with that. The physics is like Skater Theorem. It's what would Brian Boitano do, right? It's I'm spinning, I'm some vortex, I'm spinning, and at some point, if I get, let's move me inwards. If I get moved inwards and I want to stay 2D, I want to stay in a line vortex, and I also have to conserve my own mass. So then, when I move in, I stretch up. If I stretch up to conserve mass, I also have to pull in. Do you get it? Imagine it's a column or a cylinder of fluid. If I stretch it, it's got to get skinnier if it conserves its volume and mass. That make sense? Okay. Well, now I'm rotating. I'm a vortex that's rotating. I'm going to conserve my angular momentum. I'm going to conserve that. So as I move inwards, if I pull my arms in, I am Brian Boitano, right? And if I get pushed out further from the rotation axis, I'm going to get squashed, I'm going to get fatter, and I'm going to spin maybe even the other way. I'm definitely going to spin slower. Are you with me? Okay.
I have a basic question.
Go.
Why aren't those, I'm going to call them columns of stuff, why aren't they coming out radially from the center?
Good.
I don't understand that H thing.
Okay. So wait, so you mean why isn't the flow radial? Gravity is radial. Gravity is radial. We all know that. You don't fall off in Australia, right? Wherever we are locally very happy. So gravity is radial. And what's amazing is, so let me explain this picture a little more. In this picture, it's hot in the inside of the planet. It's cold on the outside. That's actually correct for planets. So the hot stuff wants to actually rise outwards. In the equator, that's moving this way. Okay. So when this blob of hot fluid, you can see it right there, there's a hot blob, a hot plume coming out, and it's going to meander its way all the way across. Here, there's a cold plume falling from the cold side. It's falling its way in. But if you look from the side, since everything is quasi-2D, because rotation is so strong, when this hot stuff moves out, it drags an entire column of fluid with it, and the entire column moves out or in. That's totally crazy, but actually that's what happens. You might say, well, yeah, but it should be different at the poles. Yeah, it is a little different at the poles. The poles are a little different. We are skipping convection at the poles today. I will come back if you want. If you people are gluttons for punishment, we will talk about polar convection someday. Okay. But the fundamental point is everything, no matter how it's moving, and actually you brought up a good point, these things are moving in and out. That's something to note. They're not just sitting there. They're moving. It's turbulent convection. It's just weirdly aligned turbulent convection. And so now we're just thinking one of those structures being somewhere out there with a height h. Are you with me?
Okay.
Good. Okay, so it's got height h. When it moves in or out, it should start spinning one way or the other. Good? Okay. Okay. Good. Oh, yeah. I hopefully said that, maybe even clearly. If you stretch it, it spins up. If you squash it, it spins down. Now, this is the really fundamental point. This one's hard. This argument holds even if none of the fluid starts out moving at all. Whoa, what am I talking about? So, let's say, remember how I said planets are spinning for billions of years? Let's imagine there was no convection. And The fluid is all just moving with the planet at whatever that rate is. Let's say none of the fluid's moving here, but I took some column of height h, this column, for instance, hand of God, just like in our video, I moved it out a little. What would happen to it? Suddenly it would turn into a vortex. There'd be no motion anywhere else. But if ever I take even fluid that starts off just sitting around smoking a cigarette, doing nothing, it's wasting its life. It's not a vortex. For me, that's a waste. But then you move it, you induce vorticity. Does that make sense? So even if it started off in this system non-rotating, the minute you displace it, it's a rotating vortex. That's why when you look at a Jupiter, you see so many vortices. Does that make sense? That's a hard point. Okay, maybe I'll skip it and we'll do something to try to drive it home. Oh, so let's try this ourselves. I need volunteers. I've never done this before, but we're going to try a people demo. Can I get lights? I forgot to ask Paul. Oh, yeah, I got a question first. Yeah, go. Go. Oh, you want demo? Okay, great. So what I need then, we'll do it down this central aisle if it works. I need 3 rows of people down the central aisle. I'd say give me, serious, I'd say give me, if you can, let's do 12 people this way with 3 rows. Can I get a 12-person row? Can I do it? Yes. I've never tried to get so many people to do a demo in my life. This is great. So you're going to make 1 row there. You're on 1 row. It may get a little tight. Yep. Good. Good. Yeah, small people are wonderful here. Good. Okay. Oh, I have no idea if this will. Yeah, let's get small people in the middle. Small people in the middle, big people on the outside. Awesome. Yes, small people. Bring it, small people. Good. I think that's fine. In fact, that's good. We're good. Okay, so now we are part of a rotating planet, this little section. I'm going to imagine that this is along some line of latitude. Are you with me? This is a latitude line. Okay, and we're wrapping around the planet. Okay, so now I'm going to make, I forgot, I made this up. You wouldn't believe I made this up. I made this up. We're going to imagine the fluid layer. We're a part of a shell. We're a part of a planet. It's getting deeper towards the moraine. Okay? So none of us are starting off rotating at all. But when you move this way, we don't need you to stretch. You can if you want, if it makes you feel better. When you move this way, you're going to feel that stretching. So which way are you going to rotate? We're going to imagine it's a right-handed planet. So you're going to move this way and start rotating this way. Do you get it? You'll spin faster. I'm going to mix you that way. This is what happens in turbulent systems. Things just kind of exchange. You're going to move that way. Which way are you going to spin? If he was spinning faster, then when you move this way, you're getting squashed. You're going to rotate slower. And you could even imagine just rotate the other way, because we started off non-rotating in the planetary system. So you're going to go right-handed, your whole row. And your row is going to move to get squashed. You're all going to be left-handed vortices. So let's all exchange places. People in the middle, stay in the middle. OK, do it. Let's do the exchange. And start your spins. Start your motors. OK, wait, sorry. And I still need 3 rows. So I need this whole row to move to that side, this whole row on that side. Good. You guys got it? So you're all right-handed. Wait, right-handed. Everybody on this side is right-handed. Yep, follow me. Is that good? Everybody on this side is left-handed. OK, now fluid in the middle. Which way would you be getting pushed? Everybody starts, these guys are all pushing on you. Which way would you tend to move? Which way are they rubbing you? You would all be going backwards. You'd be the jet. Okay, wait. Let's just keep doing it for, actually, let's take a break so these people don't get nauseous. Did everybody notice the jet? Now, wait, one more moment. Really, there'd be fluid on the other side as well. Which way would that fluid end up going? So if we just had, for some reason, an incredibly wide central aisle, we could have actually done a 5-column version, and we would have made rotating or multiple banded jets. That's Jupiter. Are you with me? Yeah, this one, I don't know if you want to call it retro or pro, I don't care. Oh, that one was retrograde, because that's a retrograde jet. If we'd had a little more room, we would have made 2 progrades. That's awesome. So you don't need all that math. You just need a lot of people who are, for some weird reason, trusting. Does everybody get it? Let's give our volunteers a hand. Did that make sense? Did that make sense? Good. Okay. That's awesome. Okay. And actually, I'll say one more thing. We could turn off the lights. Now I'm just being pedantic, but that was a model. We just made a scientific model. Did it work? Yeah, it sort of worked. Was it true? No, it was mainly me making stuff up. But it was a massively simplified version of a more complex system. It's a scientific model. And did it roughly generate a system like what we see? Yeah, good. If we wanted to make a more realistic model, we could. But that's a very 0th order scientific model. Yeah, we did the mixing. I'd never done that before. Did that work? At all? I didn't think it would. So that was the first time. You people have done that for the first time. I don't know if anyone's ever done that because it was a little bit crazy. So that's cool that we did that here first time. Okay, so Skater Theorem. It was awesome, and it created jets for us. What we didn't answer was, how wide are the jets? Why do we get 30 of them on Jupiter? We don't get 30. We get like a few of them on Earth, 3, 4, sometimes 5. Okay. So what sets how far that silly model works? The issue is, yeah, we're in a shell with curvature. If we move this person or that person, whoever I was moving, if we move them all the way over here, we'd generate so much spinning, we'd just break the system. It would say, I'm not going to be an axial vortex anymore. That was stupid. You moved me all the way across. The stretching was stronger than any other vortex anywhere on the planet. And eventually, the approximations behind this axial vortex break down. So you can't overdo it. Do you get what I mean? And so that's heuristic. But if you move someone too far, they kind of forget where they started. That's maybe a better way to say it. And then it doesn't work anymore. So that first occurs at a scale called the Rhine scale. Peter Rhines thought of this in 1975. And everyone went, oh my God, that's right. And so that scale sets the width of jets in planetary systems. Now, the real key then is, the stronger the curvature, the narrower the jet. The stronger the curvature, the shorter a distance this person or that person moves before they go, I don't even know why I'm doing this, which could be a very short distance if you're massively stretching them. So it's how far do you move before it's so much stretching that it becomes nonlinear, too complex, and the system breaks. Does that make sense? I'm again just you can see I'm hand waving wildly. There's a lot of math here. I don't see any really good reason to do it. But that's still the idea. So we could build, greater curvature means skinny jets. And so we could do this in a numerical model. And here's a model from my collaborator, Maritz Heimpel. We're looking at the back and forth. Red is prograde, blue is retrograde. He's got a thin shell of fluid, which means there's a lot of stretching in it. And he gets back and forth alternating jets. Cool. So that was a nice model of Jupiter. However, it only works in these ultra-idealized numerical models. Nobody had gotten these in experiments. And I'm deep down fundamentally a person who thinks you should be able to get things to work both on the computer and in the lab. So we tried to build one in a jacuzzi. And what we wanted was, again, a lot of stretching, a big change in the surface layer height. So the easiest way to do this on Earth, to create this really massively curved layer, was to work with French people, right? The best way to do it was these are fabulous fluid dynamicists in Marseille, Michael Labarce, Ben Favier, and Simon Cabinets. And we built this in a 4-month visit. And so instead of doing a full sphere, which doesn't work very easily on Earth, we just did, I don't know if you can see it there, but washed out. We did a huge parabola. The tank is 1 meter wide. It's about 1.5 meters high. We put it on a big table and we spun it as fast as we could before the water started spraying out massively. And Simon was like, let's do it anyways. We all argued, you're spraying the computers. He's like, I don't care, I want the data. It was like, you're gonna break the computers and not get the data. But okay, so that was 75 RPM. And we just bought, this was a big trash can. It was a big polyethylene industrial trash can. But we had the ingredients right. It didn't need to be fancy. And so then to get the turbulence, we didn't want to do convection too hard. So we put a pump in the bottom and just pumped up and down. We pumped fluid up and we sucked it down with a pump beneath a false floor. So we had big surface curvature and we had a lot of turbulence. And it's rotating at 75 RPM. Once it started working, Benjamin Favier then made a supercomputer simulation. And again, you see, even though that's, I don't know if you can see it, but this is supposed to be the back and forth flows. And they're once again red and blue. You get bands. And where there's a red band, it goes all the way through. So we've got this gyroscopic physics again. It's not a planet, but it's got all the ingredients. Turbulence, rotation, and a big curvature. Okay, so there's Michael next to the device. And here it is rotating. And so it's really big. It's behind this big screen, because if anybody touched it, it would basically just kill you. And so we have to be careful. And then we made a false floor, put a big pumping system underneath. And there's Simon with the floor. We tested in a kiddie pool. So we got a kiddie pool for the lab. And tested, are we getting turbulence? And the answer is yeah. You can hear it a little. Yeah. So we just made a bunch of up and down little turbulent jets. Those aren't, sorry, I shouldn't say jets, just little sprays in and out. Those aren't circling around any planet. They were going up and down. They were far from it. But when we start rotating them, they do turn into jets. So here's the device again. I just wanted to show we had a light source at the top and a little camera up there. But the camera up there didn't work, though I'll show you the next movies from that camera. And so instead we put a GoPro right on top of the lid that's on top of the trash can. Why did we need a lid? We need a lid because it was rotating at 75 RPM. And if we didn't have a lid on there, then the air in the room would be sitting on top of the fluid. And as far as the fluid was concerned, it'd be going minus 75 RPM. Imagine you're living in that tank. If you're living in that tank going 75 RPM and the room air is motionless, you would see it going at minus 75. The wind drag is huge. It would take over. There'd be one big retrograde jet from wind drag. That's not our point. So we had to put a lid on. And the minute we put a lid on, we got a big reflection off the top. So this is the view off that camera way up high. It doesn't see much. So, being very technical, we duct taped a GoPro onto the lid. Do you get it? Okay. And then we dropped a bunch of floaters onto our paraboloid, and we could track them. We tracked them actually with the GoPro, but I forgot to get GoPro movies from Simon. Okay? So I have this other movie. And then we tracked about 5,000 tracks, and red means fluid going faster than the tank, and blue means fluid going slower than the tank. And so out of just this up and down little pumping from beneath this false floor, it turned into fluid going round and round. Why? Because when it moves up and down, it pushes other fluid back and forth, and you get this. You get all these jets. They naturally want to live on the Rhine scale. These are Rhine scale jets. So when you see planets, in a weird way, it's not that complex. When we take the time average of all those tracks, okay, we see nice red and blue. So I don't think that's enough. Okay, we see red and blue. So Simon did a good job. He added some dye. He just threw some dye in. We're dye people. The experiment had already been running for a while. The jets were already there. And the dye quickly starts going one way and the other and one way and the other. Can you see the jets in there? Let's do it again. Let's add our solution on top. And I think where it's red, you should see fluid going faster, Gesundheit, and where it's going blue, you should see fluid going slower. And it's slowly migrating its way in. We pour it on the side, and then it kind of migrated turbulently to fill in. Oh, and as it gets into that part, it starts going the other way. You get it? That's so cool. Okay. Let's see it one more time just for kicks. I don't know why this one's there. I think I forgot to take this out. Still cool. Okay. Good. Cool. And you might say, hey, look, oh, that's, okay, so that's screwed up. You might say, hey, that looks more turbulent than a Jupiter. Yeah, it's true. We were forcing it harder than you would have actual forcing on Jupiter. Okay, and we were spinning slower too. We still got the right ingredients. We didn't get everything right. Again, it's a model. We got what we could right. Still at 0th order, I think there's similarities between our solution and the Jovian solution, right? Everybody see it? At 1st order. That's the polar view, I think South Pole, yep. And that's our solution looking from above on our paraboloid. So what do you need? You need rotating turbulence. For us, again, I'm a deep person. I believe the jets are deep. I don't know if I'm right. But in my models, they're usually deep. And you can get fairly sensible solutions. Okay. So summary, what do you see on Jupiter? You see a lot of jets and vortices. They could all be stuck in the surface layer, or they could be like 5,000 or 10,000 kilometers deep. I love that. I love that kind of dichotomy. That's so awesome that someone is so wrong. That's the greatest. That's the joy of science, right? I might be right, I might be massively wrong. But we're going to figure it out. We're all going to throw stuff at this until we figure out what's right. Juno's going to give us a lot of data to figure that out. Here's an image of the pole. I said I'd skip polar convection. That's for another day. The pole is pretty darn awesome too. That image is a couple months old. We didn't know that was there. And actually, I was trying to get our group, one sec, to put out a paper saying there'll be one large coherent vortex at the pole. And my collaborator didn't want to because he didn't want to possibly be wrong, which drove me crazy. I think we should be proud to be wrong. But put out what your theory suggests and go. And that's even better than whatever I thought. Yeah?
Why is the spacecraft named Juno?
Good. So Juno, I believe, is another name for Jupiter. And so they named the spacecraft after basically the planet it was going to visit. Yeah?
Actually, Juno's named the wife of Jupiter.
Oh, my sincere apologies. Thank you. That's why I'm here. See, I'm not afraid to be wrong. Good. Let me try it again. Juno is a wife of Jupiter. And that makes even more sense. Good. Okay. Yeah. Go.
It's really nice that Jupiter has all these colors so you can see the jets.
Yeah, it's helpful.
What makes the colors?
Yeah. So that's a really good question. So that is another of Juno's jobs. Let's go back and see. Oh, actually, you know what? I have a nice false color image. Yeah. So that was the other one I like. And so what's happening is I've said everything is perfectly 2D, but when there are vortices, there are actually net upflows and downflows. And these flows bring up new chemistry or push down. You know, they either bring up some chemistry or push down other chemistry. So then you have all this photochemistry of new materials coming up and seeing sunlight, and you get different colors depending on upflows and downflows. And so you'll typically see one coloration for prograde and a different coloration for retrograde, because retrograde typically is bringing up a little material, I think it is, and prograde's pushing down. I might have that wrong because I actually don't worry about the up and down flows. I don't do the chemistry. I've actually been at a meeting where someone said, "Where's the ammonia in your model?" And I said, "I'm just trying to get the jets." And they said, "Right, but I've got ammonia data." And I said, "Maybe someday." And they looked at me like, ugh. And it was like, we're just trying to get the water in the bathtub to make a jet. There's no ammonia in that tub. And, but that is fundamental to what you see on Jupiter. And then to me, what's just as interesting is why Saturn has so much less contrast. Saturn's got similar jets. It's got huge vortices as well. You can see these structures, but much less so. So there are differences in chemistry and probably in the fluid dynamics, kind of like your phytoplankton. Do you know what I mean?
Question. We're looking on that on a horizontal plane. But if you look at the vertical plane, could you have jets going one way and below jets going the other?
So you mean we're looking at the surface of the planet? I would say more on a spherical surface, yeah? And you're saying if we could actually cut away, what would we see? That's one of the open questions. So some of the theories suggest that you might actually have reversals at depth. So far, there was one probe, the Galileo probe, went in, I don't remember when, I think it's 95 or 97. I think the papers came out in 97. I think the Galileo probe went in 95, and it actually went into Jupiter. And it went in about 125 kilometers before it got just squeezed to death, right? I think it got too hot, and the pressure got too high. So it failed after 125 kilometers, but that's still a good amount of data. It was well below what we can sense at the surface, and the flow direction always remained the same. Now, but that doesn't really make me happy. It makes me a little happy, right? However, the planet is huge. And I'm claiming that these deep flows might go 10,000 kilometers deep. So we, within 1%, okay, it agreed with me. That's not good. We need better data. And Juno should do better. And the way Juno will do it is to measure gravity. Because if the flow really is that deep, and it's going as fast, or even close to as fast as you see at the surface, which is the idea of this two-dimensionalization, then you'll have these big, massive, deep jets. They'll actually change the gravity field. They'll centrifuge out fluid. And it should be measurable. And so one of the ideas then is if we carefully measure the gravity field, we should test the end-member arguments. Will it work? I don't know. We'll see what the data looks like. But that is the idea, is to get at that mainly with gravity. Magnetic data may help too. Heat flow data will help as well. But gravity is arguably the key. Does that help? I didn't answer your question because it's not answered yet.
Yep. What are the, since we're looking at the great red spot, what are the current theories about it and how do they fit in with your work?
Say that one more time.
How do they fit in with your work? Is there any relationship or?
So I haven't, okay, this is a good one. So we don't yet get big stable vortices in any of our deep models. And one of the ideas, and I think this is right, is that the vortices typically are more stable in the troposphere. And I don't have a good way to explain it, but, or here at least, but I have a movie. So I have it's not on here. I have a YouTube page. If you go to YouTube, SpinLab, UCLA, one of our movies is called How to Make a Pancake Vortex. That is a big pancake vortex. I think it's about, again, about 50 kilometers thick. And we show actually a turntable demo for how to make one. And that is the basic idea, is that is an interplay between stratification in the troposphere, in the cloud layer, and rotation. And when you have both those, it gets much more stable, even more stable than in a deep layer. The jets, though, are happiest, in my mind, in a deeper layer. So now you're already getting me to carve things into pieces. But if you want to see an example of it, yeah, go to my YouTube page, play with that movie, mail me when it makes no sense.
I noticed that the motion picture you had with the big omega, the red spot was stationary.
I don't actually think it's perfectly stationary. It's the way, actually, it's more that was a very short movie. I forget how many days. It's days of data. I think it's 80, but that's nothing to Jupiter. So, and the other thing you might notice is the Great Red Spot, one of the reasons it's also so long-lived, it's sandwiched between two jets. They're constantly pushing on it. So kind of like how we generated a jet here, we've got a jet on either side constantly feeding it energy. In addition, it does something else that's rather delightful. It eats smaller vortices. And when it eats them, it feels wonderful. And so both by having this drive on either side from these bands, and also by merging with smaller jets, it's constantly feeding itself. There's one other cool thing. The size of that in latitude is the Rhine scale as well. It's gotten as big as it can get. Isn't that cool? Yeah, yeah.
These vortices, they spin parallel to the axis of Jupiter. Is that right?
The ones we see here, okay, good question. So now I've had to back off. The actual vortices we see in the troposphere, they're actually radially oriented.
So we wouldn't see a matching one?
No. That's another reason that I think they're shallow structures. Do you have another question related to that? Did I actually get one right? Yes, I got one. Okay, I answered one. So that's a good point. There's another cool thing. You actually don't see symmetry on the high latitude banded structures. So the jets also don't match across. But that's not because they necessarily are local structures. That's because there's a huge metal core in the way. So the ones that live up here, they have no idea about what the one on the other side of the huge metal core is doing. And the metal core isn't taking part because there's a massive, as I said, massive magnetic field. And the magnetic field kind of locks up the flow. Try to move a piece of metal through a magnetic field. There's a huge amount of back reaction. That's what happens here too. So the flows all slow down in the metallic region, and they are not taking part in these jet flows. But that also means the high latitudes don't know about the other high latitudes. Does that make sense?
It does, but you don't find any symmetry even very close to the equator?
Very close to the equator you do. Here, let me show you. Oh, I should have made a plot showing that. So if you look in, that's a good question. So if you look, and here's a numerical model. It's not the same as Jupiter, but if you look, this jet flow is very symmetric around the equator. But then if you looked at the high latitude guys, they don't actually perfectly match with the ones down here. They're another set down here, but they're not perfectly matched. But right around the equator, yeah, it's a very symmetric flow. More symmetric than Jupiter, actually. That's because our models aren't as turbulent, I think. Our models are cute. Jupiter's not cute. Do you know what I mean? Ours are still small ball compared to an actual planet. Yeah?
Now, is that symmetry around the equator how people estimate the size of the metallic core?
Oh, good question. Thank you. Okay, good. You people. So, okay. I love coming here. So in our model, that's the case. In our model, the width of the jet is set by the structure. And we can't get around that. However, there are other people who are building structure models not using fluid dynamics. They're instead building supercomputer models or laboratory experiments where they're compressing materials and saying, well, where would this metallize? And then you build a model of the planet's gravity field and you say, well, okay, that should be at this depth. And then do we agree? We we agree. There's plus or minuses. Actually, people argue. And so the pure radial structure high pressure physicists have been fluctuating in their numbers for about the past 20 years. It used to be for Jupiter, the transition to metal was at 75% the radius of the planet. And then more recently, it headed out to like 0.85 and then 0.9. The dynamicists, when we do this stuff, we say it could be 0.95, 0.96. It's in pretty good agreement, but that's not agreement. So, and then there's this weird, it's not even weird, there's feedback. When the high pressure people release a new paper saying it's a 0.9, the people I'm working with say, oh, we'll build a model at 0.9. But actually, did I get 30 jets? Did Moritz get 30 jets in our model? No, he got like 10. 10. What an embarrassment, right? It's not actually right yet. If you go to 0.95 for this same model, the Rhine scale prediction suggests 30. So I'd like to do that, but it gets really expensive. The thinner you go, actually, the more expensive it gets. Because actually, anyway, I don't want to get into computing. But, so we think dynamically it should be 0.95-ish. The high pressure people, slightly different. And then we iterate and we argue. I always know I'm right until I'm wrong. You know how it is. In agreement with everyone else in the room. Any other questions? Yeah. Question. So I think as are we all. So the first argument is these models, the fluid is effectively very well homogenized. So then I would argue at first order on a given radial position in the planet, right, at some given height, the fluid's roughly homogeneous. That means has roughly the same properties everywhere. However, as you go inwards, one thing is definitely happening. The planet is self-compressing, right? So it's getting denser as you go inside, and that's one of the reasons as you go inside you hit metal, is that the pressure is getting just huge to get all sciencey. And so the pressure's going up, temperature's going up, and density is going up. And so as you go inwards, properties are changing. And it may well be that having that stationary core, effectively stationary, actually helps the jets equilibrate. It kind of makes them stop a bit. And that's also an open question. If I, like this model, the numerical model I was just showing you before, it didn't have a slow inner core. It didn't have a metal core that was stationary. And I think if we'd run it long enough, that would have maybe caused us problems. However, in the lab experiments we did in France, the bottom is stationary. And actually it worked even better. So I think we need that solid, metallic, slow flowing metal to give us the right solution. I don't know if that answers your question. Roughly homogeneous, the metal core may matter. Can't tell you more. Anybody else? Awesome. So if you guys are good, anybody who's still got any energy left, let's go play with experiments. I'll be there. I'm not going to run them unless you want me to run them in some way. But I would say my kid is out there, I think. He'll tell you he thinks he knows everything in the world about them. He'll help you. I'll help you, but I really want you to play with them. One hint, don't go too fast. If you really do that, you'll just mix everything. The velocities have to be slow enough that the velocities you induce aren't much faster than the rotation velocities. Do you get it? If you start the fluid moving at 50 meters per second, it doesn't care that that's rotating at half a meter per second. And you'll lose all the physics. So get out there, play with it, make a mess. Yeah?
Have you seen any meteor impacts, any effect?
So Comet, Shoemaker-Levy, forget who. Shoemaker-Levy. I forget if it had a number with it. 9? Yeah, I was going to say 7. I knew that was wrong. So Comet Shoemaker-Levy 9 hit, when was that? Was that 90s? 90-something. And the bummer was, so that was great. That was actually going to be one of the great experiments ever devised for understanding Jupiter. But it turned out of, the timing was just slightly off. And as it was basically impacting, the impacts rotated out of view. And so they got some imaging much later, a few hours later. But there was going to be basically a seismology experiment. It was going to be a beautiful seismology experiment that would have, from the way the waves propagated and structures propagated, you know what it would have been? It would have been like looking at the Sierra wave. And if you understand the Sierra wave, you can figure out how stratified and how fast the flows are in the atmosphere. You can figure out all sorts of stuff about the local atmosphere from looking at the wave. It was going to punch in and kick off a lot of waves. And by looking at the way they traveled, we could have inferred a lot of the properties of the atmosphere.
But it didn't affect the jets in the area?
No, the jets, no. That's, you're flicking it. You're flicking the ocean. Jupiter's a big dog. Do you know what I mean? I mean, yeah, no. It would have given us a lot of information. Jupiter couldn't have cared less. So, thank you guys. That was great.